My name is Diya, and this is my poster and research on the aerodynamic trade-offs for a blended wing body or BWB configuration, drag and wake mitigation at constant lift. So first, what is wake? So wake is short for a wake vortex. And to understand what that is, let's first look at how airplanes actually fly. So airplanes fly because of a force called lift, which one of the ways which is produced is because of the shape of a wing. So let's imagine that my iPad is a wing, right? A wing is flatter at the bottom and curved at the top, right? This shape is called an airfoil. So as the wing moves through the air at the bottom of the wing travels slower, air at the top of the wing travels faster. According to Bernoulli's principle, this slower air at the bottom of the wing generates higher pressure than the faster air at the top of the wing, generating lower pressure. This pressure differential, high pressure in the bottom, low pressure in the top, is what produces the upward force of lift. However, at wingtips, so at the places where the wing ends, this pressure differential does not automatically equal zero immediately, right? Air has a tendency to go from an area of higher pressure to a lower pressure. So air at the bottom of the wing wants to go on top of the wing. However, the aircraft is still moving forwards in flight. So this phenomena creates this rotational structure of air that follows behind the aircraft. This is what a wake vortex is. They are powerful rotational structures of wingtips, and they pose huge operational hazards for following aircrafts, as well as introduce a type of drag called induced drag, which is a type of drag that can be directly attributed to the production of lift in an aircraft. So a common method to mitigate wake vortices are the introduction of wingtips. Wingtips can alter the flow in two ways. The first one being that they increase the span of the wing, so making it longer, distributing the airflow over a larger distance, reducing the strength of this rollover at wingtips. And the other way you can do this is by introducing an aggressive barrier at wingtips, breaking the primary vortex into secondary, less powerful structures, hence reducing in strength. However, the addition of the wingtip also leads to an increase in a type of drag called parasite drag, which can be attributed to the actual structure of the aircraft itself. So adding wingtips increases parasite drag. Any bumps or dents in the aircraft surface also increases parasite drag. So this trade-off in reducing the strength of the wake vortex while also maintaining relatively okay amounts of parasite drag is particularly nuanced for a blended wing body aircraft configuration or a BWB. The aircrafts that you and I fly in are conventional tube and wing aircraft. So they have a tubular body or a tubular fuselage, and they have wings on its sides, right? However, how a blended wing body differs from that is that its fuselage is seamlessly blended into its wings, making it look just like one big flying wing, right? So these are often pursued for their efficiency gains. So adding wingtips that produce an excessive amount of parasite drag would defeat the purpose of using a blended wing body. So it is imperative while choosing a wingtip to explore wingtips which mitigate wake while not adding excessive parasite drag as well. So we investigated this first by creating a high aspect ratio blended wing body aircraft as a control reference. So this one right here without any wingtips. Then we added three standardized type of winglets across three geometries. So these winglets are pretty standard across the aerospace industry today and can be seen pretty often. The first one is the end plate, which can be seen with this geometry right here. The second one is the rake tip, which is that geometry right there. And the third one is the blended canter geometry right here. We use computational fluid dynamics or CFD, so we use software called SimScale to simulate the airflow that the BWB experiences in cruise. And one of the most important aspects of our methodology was normalization of our coefficient of lift. Let's take a hypothetical scenario. Let's say I fix the angle of attack of all the geometries at 6 degrees, for example. And in simple terms, an angle of attack is just how much the aircraft's wing is pitched up or pitched down. So let's say I fix that at 6 degrees, right? Since all these geometries ends are different, they would produce different forces of lift, and hence using this equation, different coefficients of lift. Now, wake vortices and the amount of drag is heavily dependent on how much lift an aircraft produces. So, at different coefficients of lift, comparing wake vortices and the drag in the aircrafts across these configurations would be pretty unfair. That's why we changed the angle of attack of an aircraft of these geometries till a normalized coefficient of lift of 0.3 was reached. From these trials that had 0.3 coefficient of lift, we extracted the force of drag and used this equation to compute the coefficient of drag. We also extracted the peak vorticity, or how strong the vortex's core is at 0.6 meters and 1 meters from the geometry itself, and we use these two values to also calculate the percentage change, which is representative of the dissipation rate of the vortex. As a reliability measure, we also conducted a mesh convergence analysis. We used two primary factors to see if our results are mesh independent, so if they're independent of the amount of cells that we used in the simulation or not. So the two measures we used were Y plus values and the percentage change. For context, a Y plus value is the exact thickness of the very first layer of mesh cells. The target Y plus value is approximately 1. This means that the mesh spacing is perfectly matched to the fluid's speed and viscosity. While the percentage change is a percentage change of the coefficient of drag between our normal mesh setting, which is around 700k cells, to our very fine mesh setting, which is around 20.1 million cells. Our target percentage change is ideally less than 5. So as you can see, all our Y plus values were exactly 1, and our maximum percentage change across these geometries was 2.6%. So these values show that our results are in fact mesh independent and hence reliable. Okay, so moving on to our results. As you can see from this figure here, adding a wingtip has drastically reduced the strength of the vortex core. You can see here that the cores of the vortex for the base geometry, so the one without any winglets, are pretty red, and you can also estimate the values according to the legend. However, I have given the exact values right there. So you can see that as you add a wingtip, you do have this less strong vortex, right? However, you can also see that with these geometries, you have a higher coefficient of drag. So you can see, as predicted, the increased surface area from the tip devices has also led to an increase in pair-side drag. And when it comes to which wingtip was the most efficient, the rake tip and the blended canted geometry demonstrated some of the most favorable conditions for blended wing body aircraft. Where the blended canted winglet excelled is near field suppression of the wake vortex, where it achieved the lowest peak vorticity at 0.6 meters from the plane. However, the percentage change between these two was 88.7%, which is still not that ideal. A better wingtip, however, was our raked wingtip, with not only our lowest coefficient of drag, but also our highest percentage change of an impressive 90.5%. So the rake tip is the most optimal configuration for BWB designs, offering that sweet spot that prioritizes rapid wake decay and overall cruise efficiency over the sheer near field suppression of the wake vortex. So in conclusion, the rake tip was the most optimal wingtip configuration for a BWB aircraft, offering a very impressive 90.5% reduction in peak vorticity, which is again representative of the dissipation rate, which you can see in this figure as well, with the rake tip having the shortest distance where the wake is equal to 0, while the base geometry still takes a longer time for the wake vortex to go to 0. Right? And it also provides the lowest coefficient of drag. And in the future of aviation, this would help with reduced aircraft distances and also just prioritizing overall cruise efficiency for blended wing body aircrafts. Thank you.